Okay, continuing section 15.1, simple harmonic motion, we've seen the displacement as a function of time is this cosine function. Well, we can get the velocity as a function of time if we remember how that's related to displacement, that velocity is the derivative of position or displacement with respect to time, dx dt. So if we take the derivative of xm times cosine omega t plus phi, we get our xm again. The cosine becomes a negative sign because remember the derivative of cosine has a negative sign. So there's a negative plus sine omega t plus phi, and then taking the derivative of the inside of the function, we get an extra omega out in front because that's multiplied by time. So the time disappears, the phase constant disappears in taking that derivative. And so the part in front is what's known as the velocity amplitude, Vm. You can think of it as the Vmax, the maximum speed that you would ever travel, because sine is going to go between -1 up to +1. That's as big as it can get. So the very largest our speed or velocity can ever get is given by the angular frequency times the maximum displacement. And similarly, we can get the acceleration by taking the time derivative of the velocity function or the second derivative of position with respect to time. And if we take the derivative once more, we go from sine to cosine. This one, the derivative doesn't have an extra negative sign. So we don't cancel out that negative, we have an extra negative there. We still again get another angular frequency, so negative omega squared xm times cosine omega t plus phi, where again, the quantity in front of the cosine is the acceleration amplitude a sub m, or the maximum acceleration is another way to look at it, because cosine will always go between -1 to +1, so the very largest acceleration we can ever get is the angular frequency squared times the amplitude max. Now, what I really appreciate in thinking about these three equations is a visual graphic representation, where we notice that if you have an extreme value in the displacement, if you're at your amplitude, either in the positive or the negative direction, that's going to correspond to zero velocity, just like we've observed before. At that max point, it's a turning point where the velocity briefly stops. The interesting thing with the acceleration is the acceleration will also be at a maximum value, the same as the position or displacement. It's just going to be with a negative sign. It's in the opposite direction. So if our spring, for instance, is at its positive max, that means its acceleration is negative with its max value. It's trying to accelerate it back down. If it's instead at a negative max, the acceleration has its positive max value, trying to get it back up again. So these three graphs are really useful in understanding the difference between position, velocity, and acceleration. So I encourage you to try to embrace them, internalize them, understand all the ins and outs with them. And one in particular that's a really useful relationship to observe is how acceleration is related to position. So notice acceleration and position, they look like mirror images of each other. And that's because they both have that cosine function. The difference is just that the acceleration is negative of the position times the angular frequency squared. And this is actually one of the hallmarks of simple harmonic motion, that in simple harmonic motion, the acceleration is proportional to the displacement, but with the opposite sign. And the relationship between the two is the square of the angular frequency, omega. All right, so with this in mind, let's take a look at another checkpoint. So it says, which of the following relationships between a particle's acceleration A and its position x indicates simple harmonic oscillation, or simple harmonic motion? Part B, for the simple harmonic motion, what is the angular frequency, assuming the unit of radians per second, which is our classic angular frequency? So I'd like you to think this through, come up with an answer to part A and B, and then we'll compare notes in just a moment. So go ahead and hit pause now. Okay, trusting you did that. Well, we know that we want this to look just like the last setup, right? Where the acceleration is proportional to the displacement. Acceleration is proportional to x directly, with a negative sign. So what looks the most to me like that is C here, right? There's a negative and the acceleration is proportional to the displacement, not the displacement squared or 1 over the displacement, but just the negative displacement. And then for the angular frequency, we would know that it's going to, well, let's double check part A first. So, it is C. For the angular frequency, it says it's A2. Why is that? Well, that's because we know that in front of the displacement is the angular frequency squared. So since that's a 4, 4 is omega squared. So we take the square root of both sides and we get a 2. Okay, so there we have it. And that's how a number of different results have been found, is by recognizing that they follow the correct form of simple harmonic motion and being able to extract variables from them. One more thing, we can apply Newton's second law to simple harmonic motion. I know we can't get away from Newton's second law. It pops up yet again. So if we go back to our classic F equals ma, for acceleration, we're going to plug in negative omega squared x, what we just got as our acceleration value. So if we pull negative out and we group the m and the omega squared with the k, we notice that this looks a lot like Hooke's law, right? Where Hooke's law is F is equal to negative kx. And so this is the exact same form. We have a negative, we have something in parentheses that's constant, and we have x. So that in parentheses is going to be our k, right? This is another instance of seeing the similar form and making it work that way for us. So simple harmonic motion is the motion of a particle when the force acting on it is proportional to the particle's displacement, but is in the opposite direction. And so if we have this linear simple harmonic oscillation, like a mass on a spring, that's a great example to think of, then we can use the Hooke's law comparison, say that k is equal to m times omega squared. And if we solve for our angular frequency, we divide both sides by m, take the square root, and we get this expression that the angular frequency just depends on the spring constant k and the mass that we've put on the end of the spring. We could also write it in terms of the period and note that the period is 2 pi times the square root of the mass on the end of the spring divided by the spring constant k. A few really key things to note with both of these equations, because they're basically the same equation, just slightly different parameter that we're solving for. But it tells us that the frequency or the period depends only on the mass and the spring constant k. There's nothing about the amplitude of the motion. There's nothing about how fast it's moving. There's just what spring are you using and how much mass have you put on the end of it. So hopefully you saw this in lab as well. This is one of the really impressive results about simple harmonic motion and about oscillations of a mass on the end of a spring. Okay, well with that we conclude section 15.1, our introduction to simple harmonic motion.